Right now, in particle physics laboratories on every inhabited continent, scientists are probing the deepest asymmetries of the universe. Asymmetries that exist, that we can measure, that we can build upon because one experiment, run in the winter of 1956 into 1957, proved they were real. Ask anyone who cracked the mystery of parity violation. They will say Tsundao Li and Chen-Ning Yang. They won the Nobel Prize for it. They are not the full answer. The full answer is Chien-Shiung Wu. And the fact that you may not recognize that name is not an accident of history. It is history's verdict on what counts as science and who counts as a scientist, a verdict that was wrong then and remains worth examining now. Chien-Shiung Wu was born in 1912 in Liu, a small town outside Shanghai, in a China that had just shed its imperial dynasty and had not yet decided what it would become. Her father, Zhang Wu, was an engineer who had helped organize the 1911 revolution, and he held an unusual conviction for his time and place, that daughters deserved the same education as sons. He founded one of the first schools in the region to admit girls, and he enrolled his daughter in it. That single decision set in motion everything that followed. Wu was exceptional from the beginning, not in the soft, anecdotal way that biographies often claim for their subjects, but in the documented, competitive, measurable way that left records. She graduated at the top of her class from the Suzhou Women's Normal School and was admitted to National Central University in Nanjing, where she studied physics. By the time she received her bachelor's degree in 1934, her reputation within Chinese academic circles was already significant enough that the president of the university personally encouraged her to pursue graduate study abroad. She sailed for the United States in 1936. She was 24 years old. She intended to study at the University of Michigan. She did not. When she arrived in San Francisco and visited the Berkeley campus of the University of California, she recognized immediately that Berkeley was where the most serious experimental physics was happening. Ernest Lawrence had just built his cyclotron there. The radiation laboratory was producing science that was reshaping what physicists thought they knew. Michigan, for all its merits, was not that. Wu changed her plans, enrolled at Berkeley, and began working under Emilio Seger, one of the sharpest experimental minds of the 20th century. Her doctoral work focused on fission products of uranium and the mechanisms of beta decay, the process by which an unstable atomic nucleus emits an electron and transforms into a different element. Beta decay sounds like an abstraction. It is not. It is one of the fundamental processes that governs matter itself, and understanding it precisely required exactly the kind of patient, meticulous, technically demanding experimental work at which Wu would spend a career excelling. She earned her doctorate in 1940. What followed should have been a straightforward academic appointment at a major research university. It was not. Wu was a Chinese woman in wartime America, and the combination of those two facts closed doors that her credentials, by any objective measure, should have opened. Berkeley did not offer her a faculty position. Princeton, which in those years did not admit women as graduate students in physics, was not an option at all. She taught briefly at Smith College and later at Princeton, not in the physics department, but in a program training naval officers. Before Columbia University finally offered her a research appointment in 1944. At Columbia, she joined the Manhattan Project's Division of War Research and made an immediate, critical contribution. The plutonium production reactors at the Hanford site in Washington were mysteriously shutting themselves down shortly after reaching full power. No one could explain it. Wu identified the cause: xenon-135, a fission byproduct with an enormous capacity to absorb neutrons, was poisoning the chain reaction. Her analysis allowed engineers to redesign the reactor to compensate. The project worked. The reactors ran. After the war, Wu stayed at Columbia. She became, in the estimation of colleagues who included some of the most decorated physicists of the century, the finest experimental physicist alive. Her specialty, beta decay, nuclear structure, the precise measurement of what happens at the subatomic level, required a combination of theoretical understanding, experimental ingenuity, and almost inhuman patience in calibration and verification. Enrico Fermi, who won the Nobel Prize in 1938 and whose opinion on experimental physics carried as much weight as anyone's, considered Wu's measurements of beta decay among the most precise ever made. Robert Oppenheimer called her the best experimental physicist he knew. These were not polite compliments. They were the assessments of men who had high standards and who knew exactly what they were looking at. In 1956, two theoretical physicists at Columbia, Tsung-Dao Lee, and at the Institute for Advanced Study in Princeton, Chien-Shiung, published a paper that asked a question that, once asked, seemed almost too strange to believe anyone had missed it. The question was this: had anyone actually checked whether the laws of physics treat left and right the same way? The principle they were questioning was called conservation of parity. It held, essentially, that any physical process and its mirror image should behave identically, that nature has no preference for handedness. This principle had been assumed, rather than verified, in the weak nuclear force, the force responsible for beta decay. Li and Yang reviewed the existing experimental evidence and concluded that there was essentially none. No one had tested it. They proposed that parity might in fact be violated, that the weak force might have a handedness, a preference. Their paper laid out the theoretical prediction. It did not test it. Testing it required an experiment, and the experiment they needed was extraordinarily difficult. To detect parity violation in beta decay, you would need to align the spins of radioactive atomic nuclei, get them all pointing in the same direction, like a collection of tiny spinning tops all tilted the same way, and then measure whether the electrons emitted during beta decay showed a preference for direction. If parity were conserved, you would see equal numbers of electrons flying out in both directions relative to the spin axis. If parity were violated, you would see an asymmetry. The catch was that aligning nuclear spins requires cooling the sample to within a fraction of a degree of absolute zero, temperatures that destroy most experimental apparatus and demand extreme technical precision to maintain long enough to gather meaningful data. In 1956, this was at the edge of what experimental physics could do. Li and Yang knew who to ask. They went to Wu. Wu agreed to take on the experiment. What followed was 7 months of work that any physicist who has attempted precision experiments at cryogenic temperatures will understand as extraordinary. She collaborated with a group of low-temperature physicists at the National Bureau of Standards in Washington, Henry Abel, Ernest Ambler, Raymond Hayward, Dale Hopps, and Ralph Hudson, who had the equipment needed to reach the required temperatures. The sample they used was cobalt-60, a radioactive isotope that undergoes beta decay. The challenge was not just cooling it to 0.01 degrees above absolute zero, but maintaining that temperature, sustaining the magnetic field that aligned the nuclear spins, and simultaneously running the detectors that would capture the angular distribution of the emitted electrons, all while keeping the entire apparatus stable enough to produce statistically meaningful results. Wu canceled a trip to China she had been planning for months. She worked through the fall and into the winter, running the experiment, checking the results, running it again. Experimental physicists develop a particular kind of skepticism about their own results. The possibility that what you are seeing is an artifact of your apparatus rather than a feature of nature is always present, and eliminating that possibility requires time and repetition. Wu eliminated it. By December 1956, she had her answer. The cobalt-60 nuclei were emitting electrons asymmetrically. More electrons came out in one direction relative to the spin axis than the other. Parity was violated. Li and Yang had been right to propose it, but the proposal was not the proof. Wu's experiment was. The results were announced in January 1957. The physics community was, by contemporary accounts, stunned. Wolfgang Pauli, who had wagered that parity was conserved, reportedly said he had difficulty believing God could be left-handed. The experiment overturned a foundational assumption about the symmetry of natural law. This was not a minor refinement. This was a crack in the foundation, and it was Wu who had found it, opened it, and measured its dimensions. In October 1957, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to Tsung-Dao Lee and Chien-Shiung for their theoretical work predicting parity violation. Chien-Shiung Wu's name was not in the citation. She was not mentioned in the announcement. She did not receive the prize. The Nobel Committee's reasoning, to the extent it can be reconstructed from public records, appears to have followed the logic that the prize recognized the theoretical insight rather than its experimental confirmation. There is precedent for this. The Nobel has been awarded to theorists whose predictions were later confirmed experimentally. But the parity violation case has a feature that makes this argument uncomfortable. The theory, by Li and Yang's own description, required experimental confirmation to be meaningful. It was explicitly a proposed test of a then unverified assumption. Without Wu's experiment, the paper was a hypothesis. With it, the hypothesis became established physics. The Nobel Committee's decision meant, in concrete terms, that the people who guessed received the prize and the person who proved was not mentioned. In a scientific culture that holds reproducible experimental evidence as the gold standard, as the thing that separates science from speculation, this was a strange hierarchy to enforce. It is also worth sitting with the demographics of the decision for a moment, not because demography determines guilt, but because patterns matter when we evaluate institutional choices. In 1957, no woman had won the Nobel Prize in Physics since Marie Curie in 1903. Wu was Chinese-born in an era when the contributions of Asian scientists to Western institutions were routinely minimized in the public record. The committee's decision to pass over her was consistent with a much broader pattern. That does not make the pattern acceptable. It makes it a system, and systems have consequences. The consequences for Wu were measured and professional. She remained at Columbia, continued producing exceptional work, and accumulated recognition that fell just short of the one prize her peers universally believed she had earned. In 1958, she became the first woman elected to the National Academy of Sciences. In 1963, she experimentally confirmed the conserved vector current hypothesis, again, a theoretical prediction that required her precise experimental verification to become established fact. In 1975, she became the first woman to serve as president of the American Physical Society. In 1978, she received the inaugural Wolf Prize in Physics. Awards accumulated, honors accumulated, and through all of it, the Nobel omission remained, a specific, named absence that her colleagues talked about openly, and that she herself addressed with a measured directness that was characteristic of her in general. She once said, in a remark that has been quoted many times because it carries more precision than rage, "There is only one thing worse than coming home from the lab to a sink full of dirty dishes, and that is not going to the lab at all." She said it in the context of discussing the obstacles women faced in science. She was not speaking metaphorically. She was speaking from experience, from decades of navigating an institution that valued her results while finding consistent ways to undervalue her. The record on whether the Nobel Committee discussed Wu's case in 1957 is not fully public. Nobel deliberations remain sealed for 50 years, and so direct documentary evidence of what was said in that room is not yet available. What is public is the record of letters and statements from her peers, who were not shy about their views. II Rabbi, another Columbia physicist and Nobel laureate, was blunt. He said Wu deserved the prize. The consensus within the experimental physics community was not a minority position. It was the majority view of the people most qualified to judge. Chien-Shiung Wu died in New York City in February 1997 at 84 years old. She had lived to see parity violation become a cornerstone of the standard model of particle physics, the theoretical framework that describes every known fundamental particle and every known fundamental force. The asymmetry she measured in a cold laboratory in Washington in the winter of 1956 is not a historical curiosity. It is embedded in the mathematical structure of how physicists understand the universe. Every time a researcher working on particle physics references the weak interactions handedness, they are working with the consequence of Wu's experiment. The name attached to it in the Nobel citation belongs to someone else. In 2021, the American Physical Society renamed its prize in nuclear physics in her honor, the Chien-Shiung Wu Prize. It is a recognition that arrives 24 years after her death and 64 years after the experiment that should have won her the Nobel. The honor is real. The timing is the point. What Wu's story asks of us is not simply to feel the injustice and move on. It asks us to look carefully at who science has historically rewarded and what it has historically rewarded them for, and to ask whether those choices reflected the evidence. In her case, the evidence is unusually clean. The theory required a test. She designed the test. She ran it. She verified the result. The theory became physics because she made it so. The Nobel went elsewhere, and the reason was not scientific. The reason was something else, and that something else has a name, even if the Nobel citation did not. She proved it. History owes her the sentence,